In 2012, a solar storm powerful enough to collapse modern civilization missed Earth by 9 days. 9. We did not survive because we were prepared. We survived because our planet happened to be somewhere else that Tuesday. Now, Solar Cycle 25 has shattered every forecast, broken multi-decade records, and produced the strongest space weather in over 2 decades. Aurora is appearing over New York. Solar wind is moving at 700 kilometers per second. And researchers just found something locked inside 12,000-year-old tree rings that suggests the sun has done something far worse before and that it's about to do it again. Something our power grids, satellites and internet are completely unprepared for. Stay until the end to understand what that is and why it matters right now. If this has you hooked, subscribe to the Skylab, because this story has more chapters coming and we will cover every one of them. Drop a comment telling me where in the world you are right now, and I want your honest read on this. Pure coincidence? Or is the universe leaving us a note we keep choosing not to open? Now, let's get into it. Part 1. The storm happening right now. Right now, while you're going about your day, Earth is being hit by a geomagnetic storm. Not a metaphor, not a simulation. An actual disturbance in our planet's magnetic field, triggered by the sun, happening at this very moment. The sky over New York is glowing. People in Washington state are stepping outside and staring upward at curtains of green and red light that have no business being that far south. And most people on Earth have absolutely no idea any of this is occurring. This is a G2 geomagnetic storm, which means it sits in the moderate range on the scale that scientists use to measure how badly the sun is shaking our magnetic bubble. Moderate sounds reassuring. Moderate sounds like something you can ignore. But here is what moderate actually looks like in practice. Radio communications are being disrupted, satellites are adjusting their orientation, airlines flying polar routes are rerouting to avoid communication blackouts, and the solar wind responsible for all of it is currently blasting past Earth at around 700 kilometers per second, which is nearly twice the typical speed of the solar wind on a quiet day. To understand what is driving this storm, you have to picture a coronal hole. On the surface of the sun, there are regions where the solar magnetic field opens outward instead of looping back, and through those openings, the sun exhales a concentrated stream of charged plasma directly into space. Earth happened to drift into one of those streams. That plasma, moving at 700 kilometers per second, slammed into our magnetosphere, which is the invisible magnetic shield that normally deflects most of what the sun throws at us. The magnetosphere did its job, but it did not do it without shaking. The KP index, which is the scientific shorthand for measuring geomagnetic disturbance on a scale from 0 to 9, is currently sitting around 6. A G2 storm corresponds to roughly KP6. That number means the disturbance is strong enough to affect power grid systems, degrade satellite navigation accuracy, and push the auroral oval, the ring around the poles where auroras normally appear, significantly further toward the equator. Which is why people in places that almost never see the northern lights are standing outside tonight with their phones out, completely baffled. And here is where it gets more interesting. The sun currently has multiple active sunspot regions rotating directly toward Earth. Sunspots are not just dark blemishes on a star's face, they are areas of explosive magnetic complexity. Places where the solar magnetic field is so tangled and compressed that energy can suddenly release in the form of a solar flare or, far more dangerously, a coronal mass ejection. Right now, there are several of these regions lined up like loaded cannons pointed in our general direction. Scientists are also tracking a filament eruption that may have already launched a cloud of solar plasma on a glancing trajectory toward Earth. A filament is a structure made of relatively cool, dense plasma suspended in the sun's corona by magnetic forces. When one erupts, it can release what is essentially a slow-moving but enormous CMEE, a coronal mass ejection, which is a term you're going to want to understand well before this story is over. If that cloud clips our magnetosphere in the next day or two, this G2 storm might not be the last notification we receive from the sun this week. Now, none of this is catastrophic. We should be honest about that. Trains are running. The internet is working. You're reading this, which means civilization has not collapsed since you started. A G2 storm is something the sun produces regularly during active periods, and our systems are built with at least some tolerance for it. But here is what this storm is actually telling us, and this is the part that the space weather community finds deeply uncomfortable. This storm is a symptom. It is evidence of a sun that is currently far more active than anyone expected it to be at this point in its cycle. Solar Cycle 25 officially began in December 2019. Before it started, a panel of experts from NASA and NOAA sat down with all available models and data and made a formal prediction. They expected a weak cycle, a quiet cycle, something resembling Solar Cycle 24, which was itself one of the least active cycles in a century. That forecast turned out to be wrong in a way that has forced the solar physics community to ask some uncomfortable questions about how well they actually understand the star at the centre of our solar system. Modern civilization is more dependent on solar weather-sensitive technology than at any previous point in human history. Every GPS signal you use, every satellite phone call, every power line running electricity to your home, every internet cable connecting continents together, all of it operates within a thin margin of tolerance for what the sun can do. We built this entire technological world during a period when the sun was relatively calm. We built it without fully accounting for what happens when the sun is not calm. And here is the thing that should make you sit with that thought for a moment. The current G2 storm is not the largest solar storm in recent history. It is not even close. In 2012, the sun launched something at Earth that was in a completely different category. Something that, had it arrived just 9 days earlier, you and I would quite possibly not be having this conversation. Not because everyone would be dead, but because the infrastructure that allows this conversation to happen might no longer exist. Part 2. The day Earth was 9 days away from disaster. On July 23, 2012, the sun did something remarkable. It launched one of the most powerful coronal mass ejections ever recorded directly across Earth's orbital path. Not toward Earth, to be very precise about this because timing in orbital mechanics is everything. It launched across the exact stretch of space where Earth had been 9 days earlier. 9 days. That is the margin between the technological civilization you are currently living inside and something that experts have described, without exaggeration, as potentially the worst disaster in modern history. A coronal mass ejection is not a solar flare, and the difference matters enormously. A solar flare is a burst of electromagnetic radiation, X-rays, gamma rays, radio waves, that travels at the speed of light and hits Earth about 8 minutes after it leaves the sun. Impressive, dangerous in its own ways, but brief. A CME is something far more physical. It is billions of tons of magnetized plasma, actual matter, ripped from the solar corona and hurled into space at extraordinary speeds. The 2012 CME was travelling at approximately 3,300 kilometers per second. To give that number some context, the fastest human spacecraft ever launched moved at around 17 kilometers per second. This thing was moving nearly 200 times faster. The event was detected not by Earth-based instruments, but by a spacecraft called Stereo-A, part of a pair of NASA probes positioned off Earth's orbital path to give scientists a three-dimensional view of the sun. Stereo-A happened to be almost directly in the path of the ejection. It measured the full force of what the sun had produced, and when scientists later analysed that data and asked the question, what would have happened if Earth had been in the way, the answers were sobering. Scientists used something called the DST index to measure the intensity of geomagnetic storms. DST stands for disturbance storm time, and it measures in nanotesla how badly a storm disrupts Earth's magnetic field. A DST reading of -50 nanotesla is considered a moderate storm. The May 2024 G5 storm, the strongest in 2 decades, produced a DST around -400 to -500 nanotesla. Scientists estimated the 2012 event could have produced a DST around -1,200 nanotesla. For comparison, the most famous solar storm in recorded history is the Carrington event of 1859. During that storm, telegraph operators across North America and Europe reported sparks flying from their equipment. Some operators disconnected their batteries entirely and found the machine still worked, powered purely by the geomagnetic currents flowing through the telegraph lines. Aurora was visible as far south as Cuba and Hawaii. The DST equivalent for Carrington is estimated around -800 to -1,000 nanotesla. The 2012 event would have exceeded it. The solar physicist Daniel Baker, one of the leading researchers who studied the 2012 data, stated clearly that if the CME had struck Earth, the damage to modern infrastructure could have been without precedent in the technological age. Insurance industry analysts have estimated that a direct hit from a Carrington-class storm could cost between $1 trillion and $10 trillion in damages, with recovery timelines stretching into years or even decades. The 2012 storm may have been stronger than Carrington. Here is the mechanism that makes these events so dangerous for modern civilization specifically. When a massive CME compresses Earth's magnetosphere, the rapid fluctuations in the magnetic field induce electrical currents in long conductors on the surface. Power transmission lines, which can stretch for hundreds or thousands of kilometers, act like antennas for these currents. The induced electricity flows into transformers at power substations, and transformers are not designed for this. They overheat, they fail, and unlike a blown fuse you can replace in 30 seconds, an extra high voltage transformer can weigh 300 tons, cost millions of dollars, takes 1 to 3 years to manufacture, and is not sitting in a warehouse somewhere waiting to be swapped in. What we're talking about, if such a storm hit today, is not a power outage you ride out with candles and a camping stove for a few days. We're talking about potential cascading grid failures across entire continents, with recovery timelines that could stretch not weeks but years. And we're talking about a world where every system that depends on electricity, water pumping stations, food refrigeration, hospital equipment, communication networks, fuel distribution, begins to degrade simultaneously. We did not avoid this in 2012 because we were prepared. We did not avoid it because our grid was hardened. We did not avoid it because some satellite detected it early and gave us time to respond. We avoided it because Earth happened to be on the other side of its orbit. That is the entirety of our margin. 9 days and the cold indifference of orbital mechanics, which raises a question that has no comfortable answer. What does the actual historical record tell us about how often the Sun does something like this? Because 2012 might not be the event we should be most afraid of. Part 3. Solar Cycle. 25's Forecast Failure. Solar cycles are measured primarily by counting sunspots, those dark regions of intense magnetic activity visible on the Sun's surface. Since the 1700s, astronomers have been tracking sunspot numbers through cycles that last roughly 11 years, moving from solar minimum, when the Sun is relatively quiet and sunspots are rare, to solar maximum, when activity peaks, and then back down again. This record gives scientists what feels like a reliable dataset. It gives them the confidence to build predictive models. It gave them the confidence before Solar Cycle 25 began to look at the evidence and forecast a weak, unimpressive cycle that would quietly peak and fade without causing much concern. That forecast has not aged well. In December 2019, Solar Cycle 25 officially began. The expert panel convened by NASA and NOAA, a group of respected solar physicists drawing on multiple independent models, predicted a peak smooth sunspot number of around 115. They expected something unremarkable. What the Sun delivered instead was a cycle that, by 2024, had already reached a smooth sunspot number near 161. The cycle exceeded its predicted peak by approximately 40% and arrived at that peak years ahead of schedule. Sunspots matter because they are surface indicators of something happening deep in the Sun's magnetic engine. Each sunspot is a region where intense magnetic field lines have punched through the photosphere, suppressing convection and creating a cooler, darker area surrounded by enormous magnetic energy. Where sunspots cluster and evolve, the magnetic complexity grows. Where magnetic complexity grows, the potential for solar flares and coronal mass ejections increases. More sunspots means more active regions. More active regions means more opportunities for the Sun to launch something in our direction. In 2024 alone, the Sun produced more than 50 X-class solar flares. X-class is the highest category on the flare intensity scale. To put that in context, during the entirety of Solar Cycle 24, which lasted from 2008 to 2019, the total number of X-class flares was significantly lower. 2024 matched or exceeded multi-decade records. One of those flares reached X9 classification, placing it among the largest solar flares recorded in the modern observational era. The Sun was not behaving like a star predicted to produce a quiet cycle. It was behaving like a star with something to prove. The cycle also produced a rare phenomenon called a ground-level enhancement. This occurs when a solar particle event is so energetic that high-energy protons actually penetrate Earth's atmosphere deeply enough to be detected by neutron monitors on the ground. Ground-level enhancements are unusual. They are a signal that the Sun has accelerated particles to near-relativistic speeds, which is a level of energetics that standard solar flares almost never reach. The fact that solar cycle 25 has already produced one is a data point that solar physicists are paying close attention to. So why did the forecast fail? The honest answer is that scientists do not fully understand the solar dynamo, which is the mechanism deep inside the sun that generates its magnetic field through the movement of electrically conducting plasma. They have models. They have competing theories. Some researchers use magnetic flux transport models, which track how magnetic field lines move across the solar surface over time. Others use helioseismology, which is essentially a technique for imaging the sun's interior by analysing how sound waves propagate through it. These are sophisticated tools, and they have taught us a great deal. But none of them predicted this. One of the complicating factors is that unusual magnetic structures appeared on the sun's surface earlier in the cycle than historical patterns would have suggested. The timing of magnetic flux emergence, the process by which magnetic field from deep in the sun rises and breaks through the surface, was off in ways that existing models did not capture. This is not a story of incompetent scientists making careless predictions. This is a story of a system that is fundamentally more complex than our current models can fully represent. And here is why that matters beyond the question of intellectual humility. If our best models cannot predict the strength of a solar cycle with reasonable accuracy, then the extreme events embedded within that cycle, the truly dangerous CMEs, the most powerful flares, the potential Carrington-level storms, are even less predictable than we thought. We cannot predict the container, which means we certainly cannot predict what the container holds. The 2012 near miss was a warning. 2024 was another warning. But both of those events are modest compared to what researchers have found preserved in the oldest natural archives on Earth. Part 4. The G5 Storm of 20. 24. The Warning Shot. In May of 2024, the Sun delivered the strongest geomagnetic storm in over 2 decades. It was classified as a G5, the highest category on the geomagnetic storm scale, a level of severity that meteorologists and space weather forecasters treat the way emergency managers treat Category 5 hurricanes, with a combination of professional respect and genuine alarm. It was the first G5 storm since Halloween of 2003, and it served as a reminder to anyone who had grown comfortable with the relatively quiet sun of the previous decade that the star at the centre of our solar system is not a stable, predictable background feature of our lives. The geomagnetic storm scale runs from G1 at the low end, which causes minor fluctuations in power grids and weak aurora at high latitudes, through G2, G3 and G4, each representing increasing severity, and then to G5 at the top. G5 storms are defined by their ability to cause widespread voltage control problems, extensive damage to power grid components, satellite surface charging, radar disruption, and complete radio blackouts in some frequency ranges. They push the aurora so far toward the equator that people who have never seen the northern lights in their lives suddenly find themselves watching them from their backyards. That is exactly what happened in May 2024. Aurora was visible across the continental United States, including Florida, parts of Mexico, and observers reported sightings from Caribbean locations that had essentially no history of geomagnetic aurora activity. Social media filled with photographs of glowing skies from latitudes that had never expected to capture such images. It was beautiful. It was also a direct demonstration of how dramatically the storm had compressed Earth's magnetosphere. Beneath that beauty, practical consequences were unfolding. Satellite operators across multiple commercial networks reported increased atmospheric drag as the storm heated and expanded Earth's upper atmosphere, forcing spacecraft to expend fuel-making orbital corrections. Some satellites experienced temporary system anomalies. The SpaceX Starlink constellation, which operates one of the largest satellite networks in low Earth orbit, announced that multiple spacecraft had been affected and were taking corrective measures. This was not a theoretical vulnerability being discussed in a research paper. This was operational disruption happening in real time, to real infrastructure, during a storm that is classified as severe, but not the strongest the sun can produce. Power grid operators across North America activated emergency procedures. Utility companies reduced the loading on long-distance transmission lines to lower the risk of transformer damage from geomagnetically induced currents. These currents flow through the grounding systems of transformers and can create a phenomenon where the transformer core saturates magnetically, causing it to overheat and potentially fail. The fact that operators activated protective measures means they took the threat seriously. The fact that major transformer failures did not occur during the May 2024 storm means either that those protective measures worked, or that the storm, for all its G5 classification, was not quite powerful enough to overwhelm systems that were actively being protected. But here is the critical point. The May 2024 storm, impressive as it was not as powerful as the Carrington event of 1859. Scientists estimate that a Carrington equivalent storm today would produce geomagnetically induced currents substantially more severe than what the 2024 event generated. And as we have already established, the 2012 CME may have had the potential to exceed Carrington. So what the 2024 storm demonstrated is not that our infrastructure handled a worst-case scenario. It demonstrated that our infrastructure handled something considerably below worst case, and that even that required active emergency intervention to prevent damage. The cost of a true worst-case scenario is difficult to calculate, in part because the calculation quickly becomes circular. You cannot easily estimate the economic damage of an event that destroys the power grid, because so much of the economic activity that would be disrupted depends on the power grid to function. The numbers that analysts have attempted to put on it range from hundreds of billions to several trillion dollars, with recovery periods measured in years. And those estimates are typically based on Carrington-class events, not on something stronger. Scientists studying the historical record have found evidence suggesting that something stronger has happened, not in recorded history, not in the era of telegraphs or satellites or power grids, but locked inside the natural record of the Earth itself, waiting to be read by researchers patient enough to look for it. The discovery came from one of the most unexpected sources imaginable, the growth rings of ancient trees, and what it revealed about the sun's past behaviour changed the way solar physicists think about the sun's future. Part 5. The discovery hidden inside tree rings. Every year a tree grows, it adds a ring. You have known this since childhood. But what you may not know is that these rings do not just record the width of a good growing season versus a bad one. They record something far stranger. They record the history of cosmic radiation striking Earth's atmosphere, because that radiation helps create a specific form of carbon called carbon-14, which the tree absorbs along with ordinary carbon as it grows. Each ring is therefore a tiny chemical archive of what the sky was doing when that layer of wood was laid down. Carbon-14 is produced when cosmic rays, high-energy particles streaming in from space, collide with nitrogen atoms in the upper atmosphere. The sun plays a central role in this process, because its magnetic field modulates how many cosmic rays reach Earth. But extremely powerful solar particle events can also produce carbon-14 directly by accelerating protons to enormous energies that then strike the atmosphere and trigger the same nuclear reactions. When that happens, the spike in carbon-14 production shows up in tree rings as a sudden, measurable jump in the ratio of carbon-14 to other carbon isotopes. In 2012, a physicist named Fusa Miyake was analysing carbon-14 records from ancient Japanese cedar trees when she found something that should not have been there. In the rings corresponding to the years 774 and 775 of the Common Era, there was a spike in carbon-14 approximately 1.2% above the surrounding baseline. That does not sound dramatic until you understand that normal year-to-year variation in carbon-14 levels is tiny, and that a 1.2% spike in a single year is essentially impossible to explain through any ordinary process. Miyake and her colleagues ruled out supernova events. They ruled out gamma-ray bursts. The most consistent explanation, supported by subsequent analysis from multiple research groups around the world, was a massive solar particle event, a solar eruption so energetic that it had flooded Earth's atmosphere with high-energy protons and dramatically elevated the production of carbon-14 across the entire planet simultaneously. The estimated magnitude of the 774 event places it at somewhere between 10 and 20 times more powerful than the Carrington event, 10 to 20 times. These events became known as Miyake events, named for the physicist who identified the first one. Further analysis of tree ring archives identified a second major event around 993 of the Common Era, also substantially larger than Carrington. Other potential candidates have been identified in the record. Each time researchers look carefully at a new section of the tree ring archive, The possibility of finding another event exists, and here is a number worth sitting with. Researchers estimate that only about 16% of the available global tree ring record has been analysed with sufficient precision to detect Miyake events. 16%. The catalogue of extreme solar events we have identified may represent a small fraction of the events that actually occurred. People alive in 774 had no way of knowing what the Sun had done. There were no instruments. There were no scientists measuring the sky's chemistry. Some chroniclers recorded unusual celestial phenomena, strange lights, unusual appearances in the heavens, but no one understood the mechanism. The event simply happened. The atmosphere briefly filled with extraordinary levels of cosmic radiation, and the trees quietly absorbed it all into their annual rings, preserving the record for over 1,000 years, until a Japanese researcher sitting with a dataset decided to look closely at the numbers. What the Miyake discovery established is not just that one extreme event occurred in 774. It established that the Sun is capable, without any warning and at apparently random intervals, of producing radiation events far beyond anything the modern world has ever measured directly. And if the 774 event was 10 to 20 times Carrington, that already raises the question of whether there is an upper limit to what the Sun can do. The answer, found preserved in material even older than those cedar trees, suggests that there may not be. Part 6. The 14,300-year event. Somewhere in the French Alps, ancient trees died thousands of years ago and fell into sediment, where they were preserved in conditions cold and wet enough to prevent the wood from fully decomposing. These are called subfossil trees. They are windows into a world so remote from our own that the people living then would not recognize a single element of modern civilization. Researchers extracted samples from these subfossil pines and sent them to multiple independent laboratories for carbon-14 analysis. What those laboratories found was not a spike, it was a wall. The event dates to approximately 14,300 years ago, placing it near the end of the last ice age, a period sometimes called the late glacial interstadial. The carbon-14 signal in those ancient rings is substantially larger than the 774 Miyake event. Independent replication across multiple labs using independent samples confirmed the finding was real and not a measurement artifact. This was not a bad day for the Sun. This was something in a category that modern solar science has never observed and has barely begun to understand. Estimating the exact intensity of an event 14,000 years ago from carbon-14 ratios requires models with significant uncertainties. But the numbers that researchers have calculated are genuinely difficult to absorb. Some estimates suggest the radiation output of the 14,300-year event may have been hundreds of times more intense than the largest solar storms recorded in the modern era. Not 10 times, not 20 times, potentially hundreds of times. If a fraction of that assessment is accurate, this was an event without comparison in anything that technological civilization has ever had to contend with. Consider what such an event would mean in practical terms for a world with our current infrastructure. Astronauts aboard the International Space Station can absorb dangerous radiation doses from large solar particle events even with shielding. During a Miyake-class event, any unprotected astronaut would face life-threatening radiation exposure within hours. During something hundreds of times more powerful, that calculation becomes academic. Satellites in orbit would face extreme particle bombardment capable of permanently damaging electronics. The atmosphere itself would experience significant ionization effects, with potential consequences for the ozone layer lasting months or years. On the surface, Earth's atmosphere and magnetic field provide substantial protection, but geomagnetically induced currents in power infrastructure would scale with storm intensity, and at the levels suggested by the 14,300-year event, the currents flowing through transformer systems would be catastrophically larger than anything modern power grids were designed to withstand. Every scenario that analysts describe when discussing Carrington-class storms would be multiplied by factors that make the modelling exercises feel inadequate. Here is something that surprised the researchers who analysed the event. It occurred during a period that appears, from other proxy records, to have been a time of relatively low overall solar activity, not solar maximum, not a period when the Sun was demonstrably churning with sunspots and active regions. The conventional assumption in solar physics is that extreme events cluster during solar maximum, when activity is at its peak. The 14,300-year event challenges that assumption. It suggests the Sun can produce extraordinary events even when it is not displaying obvious warning signs, which changes the nature of the risk calculation entirely. Stars similar to the Sun, observed with modern telescopes, have been seen producing eruptions that dwarf anything in our recorded solar history. These are called superflares, and their existence raises a question that the scientific community has not fully resolved. Is our Sun capable of producing one? If an event 14,000 years ago was hundreds of times more powerful than modern records, does that mean we have already observed evidence of a solar superflare preserved in wood? The answer to that question leads into territory that keeps solar physicists awake at night and has attracted the uncomfortable attention of people who interpret the ancient record in much more alarming ways. Part 7. Why Miyake events terrify solar physicists. The thing about Miyake events that distinguishes them from every other category of solar threat discussed in this story is not their size, though their size is extraordinary. It is not their potential consequences, though those consequences are severe enough to warrant serious attention on their own terms. What distinguishes Miyake events from ordinary space weather threats, what places them in a separate category of concern for the scientists who study them most carefully, is their apparent randomness. And in a world where the entire framework of solar storm preparedness is built on the assumption that warning is possible, randomness is the most frightening property a threat can have. Solar flares and coronal mass ejections are dangerous, but they are at least loosely predictable in a statistical sense. They are tied to the 11-year solar cycle in ways that give forecasters a meaningful framework for assessing risk. When sunspot numbers are high, and the Sun's disk is populated with complex evolving active regions, the probability of significant eruptions increases measurably. Space weather forecasters can look at a solar magnetogram on any given day, identify the active regions present, assess the magnetic classification and complexity of each one, consult the historical record of how similar configurations have behaved, and produce a probability estimate for significant flare activity in the next 24 to 48 hours. That estimate will not be perfectly accurate. The Sun will sometimes surprise even the most experienced forecasters, but the estimate is meaningfully better than random chance, and that margin above random chance is what allows grid operators, satellite controllers, and aviation authorities to make informed decisions about protective measures. Miyake events do not fit inside this framework at all. The 774 event, which left the largest carbon-14 spike in the tree ring record until the 14,300-year discovery, did not occur at a well-documented solar maximum with obviously elevated precursor activity. Neither did the 993 event. The available historical evidence does not place these events at moments when the Sun was displaying the conventional indicators of heightened danger. Some Miyake events appear, based on the proxy records surrounding them, to have occurred during periods of relatively low solar activity, the equivalent of solar minimum, when the conventional space weather risk framework would suggest the Sun is at its quietest and least threatening. From a forecasting perspective, this is not merely a gap in predictive capability, it is a fundamental failure of the entire conceptual framework that forecasting is built on. It is the equivalent of learning that a Category 5 hurricane can form from a clear blue sky with no preceding tropical disturbance, no elevated sea surface temperatures in the region, no atmospheric instability detectable by any instrument, and then simply appear at full intensity without warning. The tools you use to assess risk do not apply. The indicators you watch for are not present. The danger exists in a dimension that your monitoring systems are not measuring. The recurrence rate estimates for Miyake events are the next thing that makes solar physicists uncomfortable when they discuss this topic candidly. The current best estimate, based on the events that have been identified in tree ring records so far, suggests an average recurrence interval of roughly once per 1,000 years. That sounds like a long time. 1,000 years is 30 to 40 human generations. It is the distance between us and the Norman conquest of England, between us and the Song dynasty in China, between us and a world without printing presses, universities, or any technology more complex than a watermill. On that timescale, a once-per-millennium event feels distant enough to be someone else's problem. But that estimate rests on a foundation that is much less stable than it appears. It is derived from the number of Miyake events identified in the analysed tree ring record divided by the time span covered by that record. And here is the number that changes everything about that calculation. Only approximately 16% of the available global tree ring record has been analysed at the resolution and precision needed to detect Miyake events. 84% of the record has not been examined at this level of detail. The catalogue of identified events represents what is visible through a window covering roughly 1/6 of the available archive. If the events that have not yet been found in the unanalysed 84% occur at a similar density to those already identified, the true recurrence rate could be substantially higher than the current estimate suggests. If the actual average interval is 500 years rather than 1,000, the risk calculation changes significantly. If it is 300 years, it changes dramatically. A once per 300-year event, given that the last confirmed major Miyake event occurred over 1,000 years ago, would suggest that the next one is not centuries away. It could be decades away. It could, statistically speaking, arrive within the lifetime of people currently alive. The physical mechanism behind Miyake events remains one of the most actively debated open questions in solar physics, and the debate is genuine rather than merely academic. Multiple competing hypotheses have been proposed, each supported by some evidence and challenged by other evidence, and none has achieved the level of consensus that would allow the field to move from hypothesis to established mechanism. The first major hypothesis centers on massive solar proton events, eruptions in which the Sun accelerates an extraordinary quantity of high-energy protons and releases them in a burst that overwhelms Earth's magnetic shielding and deposits enormous quantities of radiation into the upper atmosphere, driving the carbon-14 production spike that appears in tree rings. The proton energies required to explain the magnitude of the observed spikes are well beyond anything in the modern observational record, which is part of what makes the mechanism difficult to model confidently. The second hypothesis involves magnetic reconnection on an unusually large scale. Magnetic reconnection is the process that drives ordinary solar flares. Oppositely directed magnetic field lines are forced together, break, and reconnect in a lower energy configuration, releasing stored magnetic energy as radiation and accelerated particles. In a typical solar flare, this occurs across an active region spanning a relatively small fraction of the Sun's surface. The hypothesis for Miyake events proposes reconnection events spanning magnetic structures far larger than any observed in the modern record, releasing energy correspondingly greater than anything directly measured. The challenge with this hypothesis is explaining how such large-scale magnetic structures form and what conditions allow the energy stored within them to release in a single, catastrophic discharge rather than bleeding off gradually through smaller events. The third hypothesis connects directly to the superflare research discussed elsewhere in this story. If Sun-like stars are capable of producing superflares, and if our Sun has produced something in the superflare energy range at least once in the past 14,000 years, then Miyake events might represent the lower end of the solar superflare distribution, events rare enough that the modern observational record has not captured one, but not so rare that the geological and isotopic record fails to preserve evidence of their occurrence. This hypothesis is the most debated of the three, because it requires accepting that our Sun's magnetic configuration allows for energy storage and release on scales that the current understanding of solar magnetic activity does not comfortably accommodate. The researchers who find it credible point to the 14,300-year event as evidence that something beyond ordinary solar behavior is possible. The researchers who resist it argue that the theoretical barriers to solar superflares are real, and that alternative explanations for the proxy record should be exhausted before invoking mechanisms that current solar physics does not support. What is striking about this three-way debate is not that scientists disagree. Scientific disagreement about mechanisms is normal and healthy. What is striking is that all three hypotheses share a common feature that is deeply uncomfortable from a practical standpoint. All three describe events that could occur without the precursor signatures that current monitoring systems are designed to detect. A massive solar proton event produced by a mechanism outside the normal flare-CME framework would not necessarily be preceded by the active region evolution, the magnetic flux emergence, the coronal brightening, and the X-ray flux buildup that forecasters look for before issuing alerts. A large-scale magnetic reconnection event spanning structures not currently visible in solar magnetograms would not appear in the data that AI forecasting models are trained on. A solar superflare, If the mechanism involves magnetic energy storage in configurations our instruments do not currently characterize well, might leave no detectable warning signature in any of the data streams that space weather monitoring currently collects. This is what makes Miyake events genuinely terrifying rather than merely concerning. The concern about Carrington-class storms is real, but it is a concern that fits inside an existing framework. We know roughly when such storms are more likely, during solar maximum. We know what precursor signatures to watch for. We have monitoring systems positioned to provide warning. The warning window is short, but it exists. For Miyake events, the entire architecture of warning and response that the space weather community has built over the past several decades may simply not apply. There may be no elevated sunspot count in the days before. There may be no complex active region to identify and monitor. There may be no CME tracking across the inner solar system, triggering alarms at space weather centers as it approaches. There may just be an ordinary-looking sun, displaying no unusual indicators by any measure currently available to us, somewhere in its deep interior crossing a threshold that our instruments do not monitor and our models do not predict. And then the threshold is crossed, and the event happens, and the first indication that something extraordinary has occurred arrives not as a warning but as a consequence, which is precisely where humanity stood on the morning of September the 1st, 1859, and precisely where we cannot afford to stand again. Part 8. The Infrastructure Kill Chain. Understanding why a large solar storm threatens modern civilization requires understanding exactly how the damage unfolds, step by step, because the sequence is not intuitive and it is not fast in the way that explosions or earthquakes are fast. An earthquake destroys in seconds. A hurricane announces itself over days and strikes over hours. The damage from a major solar storm unfolds over a timeline measured in minutes to hours for the initial trigger, and then in months to years for the consequences. It is slow. It is infrastructural. It operates through physics that most people have never had reason to think about. And it cascades in ways that are very difficult to stop once they begin, because each failure creates conditions that make the next failure more likely. And the systems involved are so deeply interconnected that isolating the damage requires actions that themselves cause disruption. To understand the sequence, start with what happens when a large coronal mass ejection arrives at Earth. The CME is not a wave of heat or light. It is a cloud of magnetized plasma, actual matter, billions of tons of it, carrying its own magnetic field embedded within it. When this cloud reaches Earth, it does not simply pass by. It collides with Earth's magnetosphere, the invisible magnetic shield generated by our planet's interior dynamo that normally deflects most of what the solar wind throws at us. The collision compresses the magnetosphere on the sunward side, pushing the outer boundary of our magnetic shield inward from its normal position of approximately 65,000 kilometers above the surface to as low as 25,000 kilometers, or in extreme events 15,000 kilometers. To put that compression in perspective, the geostationary orbit where communications and weather satellites operate sits at 36,000 kilometers. During an extreme storm, the magnetosphere's dayside boundary can be pushed inside geostationary orbit, leaving those satellites suddenly exposed to the full force of the solar wind, rather than sheltered within Earth's magnetic protection. This compression is not uniform and it is not smooth. It is turbulent, chaotic, constantly fluctuating, as the CME's magnetic field interacts with Earth's in a complex dynamic process that generates waves and oscillations propagating throughout the entire magnetosphere. The field lines that normally form ordered, stable structures around the planet are being shaken, stretched, reconnected and reconfigured at a rapid and irregular pace. From the perspective of a physicist, this is a fascinating and complex phenomenon. From the perspective of an electrical engineer responsible for keeping the lights on across a continent, it is a nightmare encoded in the fundamental laws of electromagnetism. The nightmare is Faraday's law, which is one of the foundational principles of classical electromagnetism and has been understood since the 19th century. Faraday's law states that a changing magnetic field induces an electrical current in any nearby conductor. The relationship is unavoidable. It is not a design flaw that engineers can root around. It is physics. During a large geomagnetic storm, Earth's magnetic field is changing, rapidly, continuously, and across the entire planet simultaneously, and Earth's surface is covered in conductors. power transmission lines stretching hundreds or thousands of kilometers, natural gas pipelines running across continents, undersea cables connecting nations, railway tracks. All of them are sitting in a changing magnetic field, and all of them are therefore experiencing induced electrical currents flowing through them, whether their operators want those currents there or not. These are called geomagnetically induced currents, and they are the primary mechanism through which solar storms damage surface infrastructure. They are not large currents by the standards of industrial power systems. A geomagnetically induced current flowing into a substation might be measured in tens to hundreds of amperes, but they are direct current, flowing continuously in a single direction, and they are entering systems that are designed to operate exclusively on alternating current. That distinction is the key to understanding why they are so destructive. A power transformer is one of the most precisely engineered components in an electrical grid. It works by using alternating magnetic flux in an iron core to transfer electrical energy between two circuits at different voltages. The iron core is designed to handle a specific range of magnetic flux densities. The alternating current that flows through the transformer's windings creates an alternating magnetic field in the core that oscillates symmetrically around zero. The core operates in a linear, efficient regime. Now introduce a direct current component from a geomagnetically induced current flowing through the transformer's grounding connection. That direct current creates a constant unidirectional magnetic bias in the core. The alternating flux that the transformer was designed to handle no longer oscillates symmetrically. During one half of each alternating current cycle, the total flux in the core, the designed alternating component plus the unwanted direct current bias, exceeds the core's design limit. The core saturates magnetically, meaning it reaches a condition where its iron can no longer support additional magnetic flux efficiently. A saturated transformer core stops working as designed. It begins drawing anomalous currents from the grid, large distorted currents that can be 10 to 50 times the transformer's normal operating current. It generates heat, because the energy that should be transferred efficiently is instead being dissipated within the core and windings. It generates reactive power, which propagates through the interconnected grid and destabilizes voltage and frequency regulation across wide areas. And if the saturation is severe enough, or sustained long enough, the transformer's internal temperature rises beyond the tolerance of its insulation systems, and it fails permanently. Not a blown fuse, not a tripped breaker. A catastrophic internal failure of a component that weighs between 100 and 500 tons is custom manufactured to the specifications of its specific substation, costs between $3 million and $10 million, and requires between 1 and 3 years to manufacture and deliver under normal production conditions. The United States currently operates approximately 2,000 extra high voltage transformers across its transmission network. These are the largest, most powerful and most critical transformers in the grid, handling the highest voltage levels and serving as the backbone of long-distance power transmission. There is no large strategic reserve of spare units. The manufacturing base capable of producing them is limited and internationally distributed. Several of the largest units used in North American grids are manufactured in facilities in Europe and Asia, meaning that a global solar storm affecting transformer demand worldwide would create a supply competition at precisely the moment when supply is most constrained. A scenario in which a major geomagnetic storm permanently damages 50, 100 or several hundred of these transformers across an interconnected grid region is not a scenario that existing emergency response frameworks are designed to address. The normal disaster response playbook, mobilize resources, clear debris, restore service, does not apply when the equipment needed to restore service has a manufacturing queue measured in years rather than weeks. The cascading consequences that follow extended grid failure stretch the imagination, not because they are exotic, but because electricity has become so deeply embedded in every system of modern life that its absence is difficult to think through completely. Water treatment plants that supply drinking water and manage sewage require continuous electrical power for pumps, chemical dosing systems, and control electronics. When grid power fails and backup generator fuel runs out, water systems begin to fail. Fuel distribution, the gasoline and diesel that power emergency generators, vehicles, and heating systems, requires electrically operated pumps at refineries, pipelines, and distribution terminals. Hospitals can sustain operations on backup generators for days to perhaps a couple of weeks before fuel supply becomes a critical constraint. Telecommunications networks require power at every relay station, every cell tower, every data center, and every switching facility. Food supply chains require refrigeration at every stage from processing facility to warehouse to retail outlet. Financial systems require continuously powered data centers to maintain the records and process the transactions that allow the economy to function. None of these systems fails instantly when the grid goes down. Each has some degree of backup capacity, some residual operational window before the power dependency becomes critical. But those windows are measured in days to weeks, not in the months to years that a major transformer replacement program would require. The scenario that solar physicists and infrastructure analysts describe when discussing worst-case geomagnetic storm impacts is not a dramatic sudden collapse. It is a slow, grinding degradation of interlocking systems, each failure compounding the difficulty of addressing others, sustained over a period long enough that the normal mechanisms of social organization and emergency response are themselves undermined by the conditions they are trying to manage. The genuinely good news, and there is some, is that this outcome is not inevitable even during a large storm. Protective measures exist, are understood, and are technically straightforward to implement. Grid operators can reduce loading on long-distance transmission lines during a storm, lowering the geomagnetically induced currents that flow through them. They can disconnect long circuits entirely during the peak of storm activity, accepting temporary service interruptions to protect equipment from permanent damage. Geomagnetically induced current blocking devices can be installed on transformer-neutral connections, interrupting the path through which damaging direct currents reach transformer cores. Some utilities in North America and Europe have implemented these measures, particularly following the 1989 Quebec event and the sustained advocacy of space weather researchers and grid engineers who have spent careers trying to elevate this issue. Many have not. The gap between what has been done to protect critical grid infrastructure from geomagnetic storm damage and what could and should be done represents one of the most consequential examples of delayed infrastructure investment in the modern era. It is not a gap born of ignorance. The engineering solutions are known, the risk is documented. The cost-benefit analysis, when conducted honestly against the potential damage, is not close. It is a gap born of the familiar human tendency to treat low-probability, high-consequence risks as less urgent than the continuous stream of immediate visible demands competing for the same resources and attention. The Sun, unfortunately, is not aware of our prioritization frameworks. Part 9. The Internet Apocalypse Scenario. The power grid is not the only critical system with a solar storm problem. In 2021, a computer scientist named Sangeetha Abdujyothi published a research paper with a title that turned heads inside and outside the scientific community in roughly equal measure. Academic papers are not typically known for their dramatic titles. They tend toward precise, cautious, heavily qualified language that accurately represents the uncertainty in the underlying research. Abdujyothi's paper broke from that tradition with a phrase that would not have looked out of place on the cover of a thriller novel. The paper examined the resilience of global internet infrastructure to severe geomagnetic storms, and the phrase it used to describe what a major solar event could do to that infrastructure was solar superstorm internet apocalypse. That is not standard academic register, and the reason it was accurate is more interesting and more alarming than the phrase itself suggests. To understand the vulnerability that Abdujyothi identified, you need to first set aside the mental model of the internet that most people carry around and replace it with the physical reality. The internet is not a cloud. It is not a wireless network floating in the atmosphere. It is not an abstract digital space that exists independently of physical infrastructure. The internet is cables. Vast, enormously expensive, physically substantial cables laid across ocean floors, threaded through mountain ranges, buried under city streets, strung between poles in rural areas, and terminated in large physical buildings full of servers, switches, and cooling systems. The wireless connections that most people use daily, the Wi-Fi in your home, the cellular data on your phone, are the last few meters of a system that is, for the overwhelming majority of its length and capacity, made of glass and copper and steel, sitting in physical locations that can be damaged by physical phenomena. The backbone of global internet connectivity is undersea fiber optic cable. There are currently hundreds of active undersea cable systems connecting every continent to every other continent, carrying the overwhelming majority of international internet traffic. These cables represent cumulative investments of hundreds of billions of dollars and decades of engineering effort. They sit on ocean floors at depths reaching several kilometers in mid-ocean sections, rising to shallower depths near coastlines where they come ashore at cable landing stations that connect the undersea system to the terrestrial internet infrastructure of each country. The data they carry travels as pulses of light through glass fibers bundled together inside a protective cable structure, and light travelling through glass is not directly affected by electromagnetic interference. The fibre itself is immune to geomagnetically induced currents in the way that a copper wire is not. This immunity is real, but it is incomplete, and the incompleteness is the core of the vulnerability. Light pulses travelling through fibre optic cable lose intensity as they travel. The glass is extraordinarily pure, and the signal loss per kilometre is very small. But over the distances involved in undersea cables, hundreds or thousands of kilometres of continuous fibre, the cumulative signal loss is substantial enough to require periodic amplification. Every 50 to 150 kilometres along an undersea cable route, a repeater unit is built into the cable structure. These repeaters receive the weakened optical signal, amplify it, and retransmit it onward. Without them, the signal would degrade to noise long before reaching the far shore. They are as essential to the cable's function as the fibre itself. Repeaters are electronic devices. They require power to operate, and that power is supplied by electrical current flowing through a conductor integrated into the cable structure, running continuously from one end of the cable to the other. This conductor is there by design and by necessity. It is the power supply line for every repeater along the cable's length, and a conductor running for hundreds or thousands of kilometres along the ocean floor, connected at each end to grounded infrastructure on land, is precisely the kind of long conductive path through which geomagnetically induced currents can flow during a severe geomagnetic storm. The same physics that makes power transmission lines vulnerable to geomagnetic storms makes undersea cable power conductors vulnerable. The fibre is safe. The repeaters that make the fibre useful are not. Abdu-Jyothi's analysis identified a geographic dimension to this vulnerability that makes certain cable routes substantially more exposed than others. Geomagnetically induced currents are stronger at higher magnetic latitudes, closer to the poles, where the geometry of Earth's magnetic field makes the induction effect more pronounced. Cables running in a predominantly east-west direction at high latitudes, which is exactly the geometry of the transatlantic cables connecting North America to Europe, experience stronger induced currents than cables running closer to the equator. The transatlantic routes are also among the highest traffic, highest capacity, most strategically important cable systems in the global internet. They carry financial transactions between New York and London. They carry the data flows that connect European users to American cloud services and American users to European ones. They carry the communications of governments, militaries, corporations, and individuals across the Atlantic at volumes measured in terabits per second. If a severe geomagnetic storm damaged enough repeater units on enough transatlantic cables simultaneously, the bandwidth connecting North America to Europe could be reduced to a fraction of its normal capacity or severed entirely. The repair timeline for damaged deep-sea repeaters is not measured in days. It is measured in weeks to months at minimum, and potentially longer depending on the location of the damage, the availability of specialized cable repair ships, and the number of simultaneous failures requiring attention. There are a limited number of vessels in the world capable of performing deep-sea cable repairs, and they are already in high demand for routine maintenance and the occasional accidental cable cut from fishing equipment or ship anchors. A scenario in which multiple cable systems experience simultaneous repeater failures across hundreds of kilometers of their length, all requiring repair at roughly the same time, would overwhelm the existing repair capacity of the cable industry. The outage duration in such a scenario would not be days, it would be months. The consequences of months-long severe degradation of transatlantic internet connectivity would extend far beyond the inconvenience of slower streaming speeds or delayed emails. Global financial markets operate on the assumption of continuous low-latency connectivity between trading systems, clearing houses, and data centers distributed across continents. The New York Stock Exchange, the London Stock Exchange, the Frankfurt Exchange, and the dozens of other financial markets that collectively set prices for assets traded globally are interconnected by these cables. the settlement systems that finalize financial transactions, the clearing systems that manage counterparty risk, the custody systems that record who owns what. All of them depend on continuous international connectivity to function. A prolonged transatlantic cable outage would not pause these systems gracefully. It would create failures, errors, and disputes in the financial infrastructure that takes months to fully identify and resolve even after connectivity is restored. Cloud computing infrastructure presents a related problem. The major cloud providers, the companies that host the computing infrastructure that a substantial fraction of the global economy runs on, distribute their data centers geographically for resilience and latency reasons, but the systems that coordinate across those distributed data centers depend on continuous, reliable international connectivity. Applications that appear to run locally on a user's device are often dependent on real-time communication with data centers on other continents. Enterprise software systems, databases, authentication systems, and the coordination layers that make distributed computing work are all built on the assumption that the undersea cables connecting them will be operational. When that assumption fails at scale, the failures propagate upward through every layer of the software stack that depends on it. It is important to be honest about what the scientific community does and does not agree on regarding this vulnerability. Abdou-Jyothi's research identified and characterized a plausible risk pathway that had received essentially no systematic attention before her paper was published. It sparked significant discussion in both the space weather and telecommunications engineering communities. But it did not produce immediate consensus. Some cable engineers have argued that the protection systems built into undersea cable power conductors and repeater electronics would prevent catastrophic failures even during a severe geomagnetic storm. They point to grounding configurations and surge protection designs that they believe provide adequate margin against the induced current levels a storm would generate. Others, including researchers who have studied the question since Abdou-Jyothi's paper was published, argue that these protection systems were designed for the ordinary range of geomagnetic variation, not for an event an order of magnitude or more beyond that range, and that the margin assumptions embedded in the designs have not been validated against extreme space weather scenarios. This debate has not been definitively resolved, and the honest answer to the question of exactly how vulnerable global internet infrastructure is to extreme geomagnetic storms is that we do not know with the precision that would allow confident engineering judgment. What we do know is that the vulnerability had not been formally studied until 2021. We know that the internet was built during a period of relatively low solar activity, when the space environment was quieter than the current cycle is demonstrating it can be. We know that the design frameworks for undersea cable systems were developed without systematic input from space weather science. And we know that the question of whether those frameworks provide adequate protection against the kind of storm that missed Earth in 2012, or the kind of event that left a carbon-14 spike in 774, has not been answered by anyone with access to the detailed engineering specifications of the systems at risk. We built the global internet during one of the quietest solar periods in a century. We connected every continent through cables whose repeaters sit in a geomagnetic environment that the sun can make dramatically more hostile. We created a global economy that depends on those connections functioning continuously. And we did all of this without formally asking whether the star our planet orbits might occasionally have something to say about our infrastructure assumptions. That question is being asked now. The answers are still arriving. And the sun, as always, is not waiting for the conversation to finish. Part 10. The conspiracy that got the fear right. When you type certain phrases about the sun into a search engine late at night, you'll find yourself in a very particular corner of the internet very quickly. The music is dramatic. The graphics are alarming. The narrator speaks with the absolute confidence of someone who has never been introduced to the concept of uncertainty. And the central claim, repeated across hundreds of videos and websites and forums, is that the sun operates on a catastrophic cycle of approximately 12,000 years, that the cycle is approaching its end, and that what comes next will make every solar storm we have discussed in this video look like a light drizzle before a tsunami. The groups promoting these ideas have built genuinely large audiences. Suspicious Observers, one of the more prominent channels in this space, has accumulated millions of views on content centered around a theorized event called a solar micronova. The theory proposes that the sun periodically, on a roughly 12,000-year schedule, suddenly expels an enormous mass of its outer layers in a catastrophic blast, one powerful enough to reshape planetary surfaces, trigger mass extinctions and collapse civilizations. Creative society and similar movements have organized around related beliefs, framing the approaching cycle end as an existential civilizational threat and calling for coordinated global preparation. Before we go any further, let us be completely direct about what mainstream astrophysics actually says about these claims. There is no observational evidence for a regular 12,000-year solar catastrophe cycle. None. The solar micronova mechanism as described in these theories is not supported by stellar physics. Our Sun is not a nova candidate in any conventional astrophysical framework. A classical nova requires a binary star system in which a white dwarf accretes material from a companion star until a runaway thermonuclear reaction occurs on its surface. Our Sun does not have a companion star actively transferring mass to it. The physics does not work in the way these theories describe. Our Sun will eventually, in approximately 5 billion years, exhaust its hydrogen fuel, expand into a red giant, and ultimately shed its outer layers in a slow planetary nebula process. That is a genuine stellar end state. It is not sudden, it is not cyclical on human timescales, and it is not what these theories are describing. So the theories are wrong. That part is clear. But here is where it gets genuinely interesting, and why simply dismissing these communities as scientifically illiterate misses something important about how they formed and why they persist. These theories did not emerge from nothing. They emerged from a real information environment in which legitimate, peer-reviewed scientific research has been establishing, with increasing clarity, that the Sun is capable of events far more powerful than anything modern civilization has ever directly experienced. The conspiratorial content and the legitimate scientific content exist in the same online ecosystem, and for someone without specialized training in solar physics, distinguishing between them requires more effort than most people have time for. Consider what a curious person encounters when they start researching solar risk online. They find real research about Miyake events, peer-reviewed studies confirming that in 774 of the Common Era, the Sun produced a solar particle event 10 to 20 times more powerful than the Carrington event. Recorded in tree rings around the world, they find real research about the 14,300-year carbon-14 spike in ancient subfossil trees from the French Alps, suggesting an event potentially hundreds of times more powerful than anything in the modern record. They find real documentation of the 2012 near miss, including quotes from actual NASA scientists describing what a direct hit might have done to technological infrastructure. They find real analysis of G5 storm impacts, real estimates of grid vulnerability, real acknowledgement from real engineers that the power systems underpinning modern society were not designed with extreme solar events in mind. All of that is real. None of it is fabricated or exaggerated in the way conspiracy content fabricates and exaggerates. And then, mixed into the same search results and recommendation algorithms, they find the micronova theory videos, which take all of that legitimate scientific concern and wrap it inside a framework that adds a regular cycle, a specific approaching date, a predetermined catastrophic mechanism, and a certainty that the actual researchers never claimed. The misinterpretation pattern is consistent enough to be almost formulaic. A legitimate researcher identifies a real anomaly. They publish their findings with appropriate uncertainty, careful caveats, and honest acknowledgement of what remains unknown. An online interpreter finds that paper strips out every qualification, amplifies the magnitude to its maximum possible interpretation, adds a cyclical recurrence pattern that the paper never suggested, and produces content that references real science while meaning something the original scientist would not recognize. The result is a strange epistemological situation. The conspiracy theories are wrong about the mechanism, wrong about the cycle, wrong about the certainty, and wrong about the timeline, but they are accidentally right that the Sun represents a genuine underappreciated risk to modern civilization. They are accidentally right that events far more powerful than modern history has recorded have occurred in the past. They are accidentally right that the infrastructure we depend on is not adequately prepared. The fear is calibrated to roughly the right magnitude. The explanation for why to be afraid is almost entirely incorrect. This matters for a reason that goes beyond the usual frustration scientists express about misinformation. When a conspiratorial explanation for a real risk becomes widely associated with that risk, it gives people who want to dismiss the underlying concern an easy exit. If the primary cultural representation of solar storm danger is videos about micronovas with ominous music and no peer review, then a scientist or policymaker who wants to avoid being associated with that content has an incentive to distance themselves from the whole topic, even the legitimate parts. The wrong explanation actively undermines the credibility of the right concern. It is one of the more frustrating dynamics in science communication, and solar risk is far from the only field where it operates. The actual risk that solar physicists describe is fundamentally different in character from the cyclical catastrophe narrative, and the difference matters enormously for how you think about it. The real risk is not a scheduled event. The real risk is stochastic, which is a technical way of saying randomly distributed in time, with a probability that does not depend on where you are in any particular cycle. A Miyake-class solar particle event does not become more likely because 12,000 years have passed since the last large event. The sun does not have a countdown clock. What the historical record tells us is that events of various magnitudes occur with certain average frequencies, and that the most extreme events, while rare, are not so rare that they can be dismissed as theoretical curiosities. Think of it this way. If you knew that a particular stretch of highway had a serious accident roughly once per decade on average, you would not conclude that the road is safe for the 9 years following an accident. You would conclude that the road requires attention continuously, because the next accident does not schedule itself to arrive conveniently after a suitable waiting period. The solar risk works the same way. A Miyake-class event occurring in 774 does not reduce the probability of another one occurring in 993, and the fact that one occurred in 993 does not mean the next one is safely distant. The recurrent statistics suggest roughly one event per 1,000 years on average, with enormous uncertainty in that estimate, and no cyclical structure that would make any particular future decade safer or more dangerous than another. This stochastic character is actually more demanding from a preparedness standpoint than a predictable cycle would be. If there were a known date, you would prepare for that date. Since there is no known date, the appropriate response is to build resilience into infrastructure continuously, as a permanent feature of how modern societies manage critical systems, not as a crisis response triggered by an approaching deadline. The event might come in 300 years, it might come in 30, it might come before this solar cycle ends. The tree ring record does not tell us when. It tells us that it will eventually happen, and that when it does, it will be larger than our recent experience has prepared us for. The conspiracy theories, for all their scientific inaccuracy, tapped into something real. People sensed correctly that mainstream discussions of solar risk were not adequately capturing the magnitude of what the historical record suggests is possible. They sensed correctly that the official reassurances about space weather preparedness were incomplete. They found communities that validated those instincts, even if those communities then took them somewhere scientifically indefensible. The underlying instinct was sound, the framework it was handed was not, and that gap between a legitimate concern and the scientifically accurate language needed to express it is exactly the space where the best and worst science communication either succeeds or fails. Which makes what researchers are now doing to monitor, model and prepare for solar extremes not just a scientific project, but a communication one. Because a risk that people understand incorrectly is almost as dangerous as a risk people do not understand at all. Part 11. The New Solar Monitoring Era. For most of human history, the first warning of a major solar storm was the storm itself. There was no early alert system, no satellite upstream of Earth measuring what was coming, no network of scientists watching a dashboard and drafting emergency notifications. Telegraph operators in 1859 did not know what was happening when their equipment began sparking and catching fire. They knew something was wrong. They could see that something was wrong. But they had no framework for understanding that a star 93 million miles away had launched billions of tons of magnetized plasma at their planet, and that the invisible magnetic field surrounding Earth was now shaking in response. The first hint of the disturbance was the disturbance. The warning and the event were the same thing. That remained largely true for longer than you might expect, even after the development of radio astronomy, even after the space age began and satellites gave scientists new tools for observing the sun. The warning window for major geomagnetic storms was measured in hours at best, and hours, it turns out, is not always enough. Grid operators managing large power transmission networks need time to reduce loading on vulnerable transmission lines, time to coordinate across utility boundaries, time to activate protective procedures that cannot be safely rushed. When the warning arrives with the storm, or just minutes ahead of it, the choices available to those operators shrink to almost nothing. You can watch it happen, or you can react after the fact. Neither is the same as being prepared. The 1989 Quebec blackout is the reference event that solar storm preparedness discussions always return to, and for good reason. A G5 geomagnetic storm caused the complete collapse of the Hydro-Quebec power grid in approximately 90 seconds. 6 million people lost power. The blackout lasted 9 hours. Transformers were damaged. The event caused over $500 million in direct damage and economic losses estimated in the billions. And critically, grid operators had limited warning and limited ability to act on whatever warning they did have. The storm arrived faster than the response capacity of the systems it struck. That event reshaped how utility companies and space weather agencies thought about the relationship between forecasting and infrastructure protection. It demonstrated concretely and expensively that the gap between knowing a storm is coming and being able to do something about it is not a gap you can afford to leave open. The current generation of solar monitoring infrastructure represents a genuinely substantial improvement over what existed at the time of the Quebec event, and even over what existed a decade ago. The backbone of near-Earth space weather monitoring is the DSCO-VR spacecraft, which operates at the L1 Lagrange point, a gravitationally stable location approximately 1.5 million kilometers directly between Earth and the Sun. DSCO-VR measures solar wind conditions in real-time, speed, density, magnetic field direction and strength, and transmits that data continuously to NOAA's Space Weather Prediction Center. When a CME, or a high-speed solar wind stream, passes DSCO-VR, scientists on Earth know that whatever DSCO-VR just measured will arrive at Earth's orbit in roughly 15 to 60 minutes, depending on the speed of the solar wind at that moment. 15 to 60 minutes is better than nothing. It is significantly better than the 0-minute warning that telegraph operators had in 1859. But to put it in operational terms, 60 minutes is approximately the time it takes a grid operator to make a series of phone calls, reach decision makers at multiple utility companies, and begin, not complete, but begin, the process of reducing transmission loading to protect vulnerable transformers. For a fast-moving CME, the warning window can compress toward the lower end of that range. For a CME travelling at 3,300 km per second, like the 2012 event, the transit time from DSCO-VR to Earth would be measured in minutes, not hours. The monitoring works, the warning is real, but the margin is thin. SWFO-L-1, a more recently launched spacecraft, supplements DSCO-VR's capabilities and provides critical redundancy for the L1 monitoring position. This redundancy matters more than it might initially seem. DSCO-VR is not a young spacecraft. It was launched in 2015 and has been operating in a demanding radiation environment for a decade. Space weather monitoring infrastructure that depends on a single aging spacecraft at a single point in space is monitoring infrastructure with a single point of failure. SWFO-L-1 addresses part of that vulnerability by ensuring that the loss of one sensor does not blind the entire early warning system at the moment it is most needed. NOAA's Space Weather Prediction Center in Boulder, Colorado, and the European Space Agency's Space Weather Service network both operate around the clock, staffed by forecasters who synthesize data from multiple instruments, update storm watches and warnings continuously, and push alerts to a distribution list that includes electric utilities, satellite operators, aviation authorities, airlines flying polar routes, pipeline operators, and government agencies. The infrastructure for space weather awareness is more sophisticated today than it has ever been in human history. The question that this sophistication raises rather than answers is whether it is sophisticated enough for the events at the tail end of the solar threat distribution. The most significant potential leap in warning capability, however, is not an improvement to existing L1 monitoring. It is a fundamentally different observational geometry. The ESA Vigil mission, planned to operate near the L5 Lagrange point approximately 60 degrees behind Earth in its orbital path around the Sun, would give space weather scientists something they have never had before: a sustained, continuous view of the Sun from the side. To understand why this matters, consider how the Sun's rotation works from Earth's perspective. Active regions, sunspot groups, complex magnetic structures capable of producing major flares and CMEs rotate into view from the Sun's eastern limb and rotate out of view beyond the western limb over a period of roughly 2 weeks as the Sun completes approximately half a rotation relative to Earth. When an active region disappears beyond the western limb, Earth-facing instruments lose sight of it entirely. If that region produces a major CME directed toward Earth, the first warning arrives when the CME reaches DSCO-VR, potentially days after the eruption, but only minutes before Earth impact. From the L5 vantage point, Vigil would be looking at the Sun's western face directly. An active region that has rotated out of view from Earth's perspective would be fully visible to Vigil for days before it could threaten Earth. Scientists estimate that this geometric advantage could extend useful CME warning times from the current 1 to 2 hours to 4 to 5 days. That is not an incremental improvement. That is a transformation of the operational planning window for everyone whose infrastructure is vulnerable to solar storm effects. 4 to 5 days changes the nature of the response entirely. A grid operator with 4 days of warning does not make emergency reactive decisions. That operator executes a prepared protocol, systematically reducing loading on vulnerable high-voltage transmission lines, coordinating pre-planned protective shutdowns in sequences that minimize disruption, and doing all of this according to procedures that have been rehearsed rather than improvised. A satellite operator with 4 days of warning has time to adjust orbital parameters, reorient spacecraft to present minimal cross-section to energetic particle flux, reduce electrical charging sensitivity, and in some cases maneuver to safer orbital regimes. Airlines have time to reroute polar flights in an orderly, coordinated way, rather than diverting mid-flight. Pipeline operators have time to monitor and manage induced current effects. The difference between 4 days and 40 minutes is the difference between a system operating at the edge of its capacity and a system that has time to act intelligently. The political recognition of space weather as a serious national and international security concern has grown substantially in recent years. Both the previous and current administrations in the United States have maintained formal frameworks treating space weather preparedness as a federal priority, with assigned responsibilities across multiple agencies including NOAA, NASA, the Department of Energy, the Department of Homeland Security, and the Department of Defense. NATO member nations have discussed space weather resilience as a component of critical infrastructure protection, recognizing that a severe solar storm affecting North America would simultaneously affect European power grids, satellite systems, and communications infrastructure. The understanding that this is a shared, borderless risk requiring coordinated international response has moved from academic papers into policy documents and operational planning frameworks. This is genuine progress, and it deserves acknowledgement without qualification. 20 years ago, space weather preparedness did not appear prominently in national security frameworks. Today it does. The monitoring is better, the forecasting is improving, the policy attention is real, and missions like Vigil represent serious investment in the warning capability gap that has been identified as the most critical operational vulnerability. And yet, warning is only one half of the preparedness equation. It is the half that tells you something is coming. The other half is what you can actually do when you receive that warning, and that half depends entirely on what resilience has been built into systems in advance of the warning arriving. A 4-day warning of a Carrington-class storm gives power grid operators time to protect transformers, but only if those transformers have geomagnetically induced current protection systems installed. It gives satellite operators time to maneuver, but only if their spacecraft carry sufficient fuel reserves for unplanned orbital adjustments. It gives internet infrastructure managers time to take precautions, but only if precautions are technically possible with the equipment currently deployed. Warning amplifies resilience. It cannot substitute for resilience that does not exist. And for the largest events in the solar threat distribution, the Miyake-class events, the 14,000-year events, the things that tree rings remember and instruments have never measured, the question of whether any warning system or any resilience investment would be sufficient remains genuinely, uncomfortably open. Part 12. The New Class of Superflare Stars. astronomers hunting for planets around other stars have stumbled onto something that was not on the original agenda. This is, it turns out, one of the more reliable patterns in the history of science. You point a powerful instrument at the sky for a purpose, and the sky hands you something you were not looking for and did not expect. The Kepler Space Telescope, launched in 2009 with the specific mission of detecting planets around other stars by measuring the tiny, periodic dips in starlight that occur when a planet passes in front of its host star, accumulated one of the most extraordinary astronomical datasets ever collected. Over several years of continuous observation, Kepler measured the brightness of more than 150,000 stars with a precision and cadence that had never been achieved before. It was designed, from first principle to final engineering specification, to find planets. What it also captured, as an inevitable side effect of staring at so many stars so continuously and so precisely, was something that changed how solar physicists think about the star in our own backyard. The dataset contained flares, enormous numbers of them, from enormous numbers of stars spanning an enormous range of energies, and within that catalogue researchers identified a category of stellar eruption so far beyond the scale of ordinary solar flares that it required a new name and a new conceptual framework to describe: superflares. The term refers to flare events on solar-type stars that release energies between 10 to the 33 and 10 to the 38 ergs. To give those numbers some grounding, the largest solar flares ever recorded in the modern observational era release on the order of 10 to the 32 ergs. A superflare at the low end of the defined range is therefore roughly 10 times more energetic than the largest flare our Sun has produced in recorded history. A superflare at the high end of the range is 10 million times more energetic. 10 million! That is not a difference of degree, that is a difference of category. These events produce brief but dramatic increases in a star's total luminosity. A superflare can brighten a star by a fraction of a percent to several percent over a period of minutes to hours, a variation large enough to be clearly detected in Kepler's photometric data and unmistakable against the normal background of stellar variability. They are violent, they are energetic, and they are, from the perspective of any planet orbiting close enough to feel them, profoundly significant events. The question that immediately arises when you encounter superflare data for the first time is obvious. What kind of stars produce these things? Exotic, rapidly spinning magnetic monsters far outside the category of ordinary stars? Unusual binary systems with abnormal configurations? Something clearly unlike our Sun? The answer, which is the reason superflare research became immediately relevant to solar physicists rather than remaining a curiosity for stellar astronomers, is that superflares are not confined to exotic stellar types. They occur on stars that are, by every standard observational criterion, Sun-like. Same spectral classification, same surface temperature range, same mass range, same luminosity range. In 2012, a research team led by Hiroyuki Maehara published findings in the journal Nature, identifying over 165 superflares on Sun-like stars in the Kepler dataset. These were not marginal detections requiring generous interpretive latitude. They were clear, well-characterized events on stars that, if you observed them without the flare data, you would classify as ordinary solar analogues without hesitation. Subsequent analyses using expanded Kepler datasets and additional data from other space observatories have confirmed and extended these findings. The more data researchers accumulate, the more clearly the picture resolves. Sun-like stars produce superflares. The frequency is low. These are not daily occurrences on any individual star, but across a population of thousands of observed stars over multiple years, the statistical signal is unambiguous. Stars that look like our Sun are capable of producing eruptions that have no analogue in anything the modern Sun has been directly observed to do. Understanding why superflares occur requires going somewhat deeper into the physics of stellar magnetic fields than the 11-year solar cycle discussion demands. The energy released in any stellar flare comes ultimately from the magnetic field. Specifically, it comes from the process of magnetic reconnection, in which oppositely directed magnetic field lines are forced together, break, and reconnect in a lower energy configuration, releasing the stored magnetic energy as electromagnetic radiation, heat, and accelerated particles. The total energy available for release in a flare is therefore limited by the total magnetic energy stored in the active region where reconnection occurs. Larger stored energy means potentially larger flare. Superflares are believed to require the presence of extraordinarily large star spots, the stellar equivalent of our sunspots, which serve as the surface signatures of the unusually strong and complex magnetic field configurations that can store superflare scale energy. Some theoretical models suggest that a superflare requires a large-scale, coherent magnetic region of extraordinary field strength, organized across a spatial scale much larger than typical solar active regions. The star spots associated with superflare-producing stars are, in some cases, estimated to be tens to hundreds of times larger than the largest sunspots ever observed on our Sun. These are not features at the margins of solar-type stellar behavior. They are features at the extreme end of a distribution that our Sun currently occupies closer to the middle. This is where the uncomfortable debate about our own Sun enters the picture and refuses to leave quietly. The Sun's current magnetic configuration, as best as researchers can characterize it from available observations and models, appears to make it less susceptible to superflares than many of the observed flaring stars in the Kepler dataset. One of the key factors is rotation rate. Stars rotate faster when they are young and gradually slow as they age, shedding angular momentum through their stellar winds. Faster rotation drives stronger magnetic activity, larger star spots, more complex and energetic magnetic field configurations. Our Sun, at approximately 4.5 billion years old, rotates relatively slowly, completing one rotation every 25 to 35 days depending on latitude. Many of the superflare-producing stars in the Kepler data rotate significantly faster, some completing a rotation in just a few days. Faster rotation, stronger magnetism, larger star spots, higher superflare probability. The logic is internally consistent. Some researchers look at this rotation-activity relationship and conclude that the probability of our Sun producing a true superflare is low enough to be effectively negligible on timescales relevant to human civilization. Our Sun is old, slowly rotating, and magnetically moderate by the standards of the superflare-producing population. This is a reasonable position, grounded in real physics, and it represents mainstream thinking in much of the stellar astrophysics community. If you ask a room full of solar physicists whether they expect the Sun to produce a superflare in the next century, the majority will say no, and they will have substantive scientific arguments to support that answer. But there is another group in that room, smaller in number but not dismissible in scientific standing, who point to the 14,300-year event preserved in ancient subfossil tree rings from the French Alps, and argue that something genuinely extraordinary happened then, and that the theoretical framework suggesting our Sun cannot produce such events needs to be held somewhat more lightly than the confident dismissals imply. The carbon-14 spike from 14,300 years ago is not explained cleanly by any mechanism that stays comfortably within the ordinary range of solar behavior. If it was a solar particle event, and the evidence points strongly in that direction, then it was an event at a scale that challenges the assumption that our Sun's slow rotation and moderate magnetic activity permanently exclude it from the superflare regime. The uncertainty here is genuine, and it is not the kind of uncertainty that more data will quickly resolve. Detecting superflares on other stars requires only that we observe the star's brightness change. Attributing the 14,300-year carbon-14 spike to a specific solar mechanism requires modelling an event that occurred before recorded history, using proxy records with inherent uncertainties, and extrapolating from a physical understanding of the Sun that is sophisticated but demonstrably incomplete. The error bars are real and they are large. What is not uncertain is the consequence side of the equation. A solar superflare releasing even the lowest end of the defined superflare energy range, 10 to the 33 ergs, approximately 10 times the energy of the largest modern solar flare, would interact with Earth's magnetosphere, ionosphere, and surface infrastructure in ways that no engineering specification currently in use was designed to account for. The geomagnetically induced currents in power transmission lines would be generated by a magnetic disturbance far beyond the Carrington scale. The radiation environment for satellites in all orbital regimes would be outside the bounds of any shielding or protection system currently deployed. The atmospheric ionization effects could persist for months rather than hours, with consequences for chemistry, communications, and potentially climate that are difficult to model with confidence. We're discussing a class of event where the question is not whether infrastructure would be damaged. The question is whether any of it would continue to function at all. And somewhere in the French Alps, in wood that grew and died before the last ice age had fully ended, the chemical record of carbon-14 suggests that the sun has already been in this territory. Not in a story, not in a theory. In the atoms of an ancient tree that absorbed what the sky was doing 14,300 years ago and held onto the evidence until we are finally smart enough to read it. Whether that evidence describes a super flare, an extreme Miyake-class event by a different mechanism, or something else entirely that solar physics has not yet fully characterized, the message embedded in those carbon ratios is the same. The sun's range is wider than the modern record shows, and the modern record is all we built our civilization around. Part 13. AI is now predicting solar storms. The traditional approach to solar flare forecasting works something like this. An experienced space weather forecaster arrives at their workstation, pulls up the latest solar magnetograms, detailed maps of the magnetic field, strength and polarity across the sun's visible surface, and begins the process of assessment that their training and experience have prepared them for. They identify active regions, those clusters of sunspots and complex magnetic structures, where the field lines are sufficiently tangled and energetic to produce eruptions. They evaluate the magnetic classification of each region, using a standardized scheme that describes the complexity of the field configuration. They consult historical statistics about how often regions with similar classifications have produced flares of various magnitudes. And then they issue a probability forecast, typically covering the next 24 to 48 hours, that gets distributed to utilities, satellite operators, aviation authorities, and anyone else whose operations might be affected by what the sun does next. This process has genuine value. It represents decades of accumulated knowledge about how solar active regions behave, encoded into a systematic practice that has been refined through continuous comparison of forecasts against outcomes. The quality of the underlying data has improved substantially as magnetograph technology has advanced, giving forecasters sharper, more detailed images of the magnetic field structures they are assessing. The statistical databases underpinning probability estimates have grown larger and more comprehensive. A space weather forecaster in 2025 is working with significantly better tools than their counterpart in 1995, and the forecasts they produce are correspondingly more reliable for the most common categories of solar events. But the forecast skill for the events that matter most, the largest, rarest, most consequential eruptions, remains limited in ways that the space weather community is honest about when pressed. The core problem is that the most dangerous solar events are also the most statistically unusual, and statistical methods built on historical frequencies perform poorly at the extremes of any distribution. When an active region is doing something it has rarely or never done before in the observational record, the historical statistics do not provide reliable guidance. The forecaster is extrapolating beyond the range of the data, which is exactly the situation where extrapolation is least trustworthy. The events that could genuinely threaten modern infrastructure, the Carrington-class storms, the potential Miyake-class particle events, are precisely the events for which the traditional statistical approach has the least to offer. Artificial intelligence is beginning to change this picture, and it is worth being precise about what that means. The progress is real. It is also incremental rather than revolutionary, and the gap between what AI forecasting systems can currently do and what would be needed to reliably predict the most extreme solar events remains substantial. But the trajectory is meaningful, and understanding where AI is genuinely adding capability versus where it is reaching the limits of what pattern recognition can accomplish matters for assessing how prepared we actually are. Machine learning models trained on years of solar magnetic field measurements and the historical record of flare events can identify subtle patterns in the structure and evolution of active regions that human analysts either would not notice or could not systematically account for when processing the volume of data that modern solar observatories produce. The human visual system is remarkably good at pattern recognition in familiar contexts, but it has bandwidth limitations. A deep learning model can process thousands of magnetogram images, identify statistically reliable precursor signatures across that entire population, and apply what it has learned to new images in milliseconds. For the common, well-represented categories of solar events, this capability translates into measurably improved forecast accuracy compared to traditional statistical methods. The specific architectural approaches that different research groups have pursued vary considerably. Some models use convolutional neural networks applied directly to magnetogram images, treating the solar flare prediction problem as structurally similar to the image classification tasks, where deep learning first demonstrated its most impressive capabilities. These models learn spatial patterns in the magnetic field distribution, particular configurations of polarity boundaries, specific arrangements of high-gradient regions that correlate with subsequent flare activity. Others use recurrent neural network architectures, including long short-term memory networks and transformer-based models that process sequences of magnetogram images over time, capturing how active regions evolve over hours and days, and identifying dynamic signatures in that evolution that precede eruptions. A region that is growing rapidly, developing new polarity complexity, or showing specific patterns of flux emergence may behave differently from a region with the same instantaneous magnetic configuration that has been stable for days. Time series models can capture that distinction in ways that single image classifiers cannot. Still, other approaches combine multiple data streams simultaneously, integrating magnetogram images with ultraviolet observations of the solar corona, X-ray flux measurements from GOES satellites, and data from heliosysmology instruments that probe the sun's subsurface structure. The rationale is straightforward. No single observable tells the complete story of an active region's energy state and eruption potential. A model that can synthesize information across multiple physical diagnostics simultaneously should, in principle, develop a more accurate and complete picture of solar conditions than any single-channel approach. Several research groups at NASA, the European Space Agency, and university laboratories have published results showing that these multi-channel deep learning systems demonstrate measurably higher accuracy than traditional statistical methods for certain categories of flare prediction, particularly for the common M-class and X-class flares that occur frequently enough during active solar cycle phases to provide adequate training data. The operational implementation of AI forecasting tools is proceeding carefully, and the caution is appropriate. NOAA's Space Weather Prediction Center and equivalent agencies in Europe and Japan do not replace human forecasters with machine learning outputs. They use AI tools as one input among many, with human experts maintaining interpretive authority over final forecast products. This hybrid human-AI approach reflects both the genuine capabilities of current systems and an honest acknowledgement of their limitations, because those limitations are as important to understand as the capabilities. The fundamental constraint on machine learning forecasting in any domain is the requirement for large, representative training datasets. A deep learning model learns to recognize patterns by being shown thousands or millions of examples of those patterns, along with the outcomes that followed. The model generalizes to new situations by finding similarity to patterns it has seen before. This works extraordinarily well when the new situation is genuinely similar to something in the training data. It fails, sometimes quietly and without obvious warning, when the new situation is outside the distribution of the training examples. Solar flares and CMEs exist on a distribution that spans many orders of magnitude in energy. The common events, C-class and M-class flares, are well represented in any training dataset drawn from the past 2 or 3 solar cycles. X-class flares are rarer, but still numerous enough to provide meaningful training signal for models focused on the upper end of the routine range. But the truly extreme events, the flares and particle events at the level of the 2012 CME, the Carrington event, the Miyake-class eruptions, are either absent from the modern observational record entirely or represented by 1 or 2 data points that are insufficient to train a model on. You cannot teach a neural network to recognize the precursors of an event that has never appeared in its training data. This is called the rarest event problem, and it is not a limitation specific to solar forecasting. It appears wherever machine learning is applied to low probability, high consequence outcomes, financial market crashes, pandemics, infrastructure failures. The events that matter most are the events the models are least equipped to handle. The best current forecasting systems address this limitation by combining AI pattern recognition with physics-based models of solar magnetic field evolution, using each approach to compensate for the weaknesses of the other. The physics-based models, numerical simulations of how magnetic flux evolves, how current sheets form, how energy builds in active region configurations, provide a framework grounded in the actual mechanics of what the Sun is doing rather than in statistical correlation with past observations. They can, in principle, extrapolate to conditions outside the historical record because they are built on physical laws rather than empirical patterns. The AI models complement this by identifying subtle observational signatures in real data that physics simulations might not capture or might weight incorrectly. The combination of physical understanding and empirical pattern recognition represents the current frontier of operational space weather forecasting, and it is producing real improvements in forecast reliability for the events that fall within its effective range. But there is a philosophical limit to this entire enterprise that deserves to be named clearly, because it defines the boundary of what technology can and cannot provide. For Miyake events, the truly extreme solar particle events that appear to occur randomly outside the normal framework of solar cycle activity, potentially through mechanisms that are qualitatively different from ordinary solar flares, it is genuinely unclear whether even the most sophisticated AI forecasting system currently conceivable would provide meaningful advance warning. If these events arise from physical processes that leave no detectable precursor signature in the observables that current instruments measure, then no pattern recognition system, however powerful, will find a pattern that is not there. If the mechanism is fundamentally different from ordinary solar eruptions, a model trained on ordinary solar eruption precursors is looking for the wrong thing in the wrong data. What Miyake events may ultimately require is not better algorithms applied to existing data. They may require a deeper theoretical understanding of the rarest and most energetic solar phenomena, an understanding of the physical conditions under which the Sun can produce events orders of magnitude beyond its typical range, built from first principles rather than from correlation with a historical record that does not contain those events. That kind of understanding requires theoretical progress that no amount of pattern recognition in existing datasets can substitute for. It requires knowing not just what the Sun tends to do, but why, at the deepest level of solar physics, it occasionally does something entirely different. And that question, the most important question in the entire field of space weather science, remains open. Part 14. The growing satellite risk. Somewhere above you, right now, there are approximately 10,000 active satellites in orbit. 10,000. That number would have been unimaginable to the engineers who designed the first artificial satellites in the 1950s, and it would have seemed implausible even to space industry analysts working just 15 years ago. The transformation has been rapid, driven primarily by the commercial satellite revolution, and it shows no signs of slowing. SpaceX's Starlink constellation has already launched several thousand satellites and has regulatory approval and stated ambitions for tens of thousands more. Amazon's Project Kuiper is in active deployment. OneWeb, now operating under Eutelsat, is adding to the total. The military and intelligence agencies of the United States, China, Russia, and other nations maintain their own fleets of reconnaissance, communications, and navigation satellites. Weather satellites watch storm systems develop over oceans. Scientific satellites monitor glaciers, measure atmospheric chemistry, and track sea level changes. And threading through all of it, providing the timing and positioning signals that an extraordinary range of modern systems depend on, are the GPS navigation satellites that have become as fundamental to daily infrastructure as electricity or running water. This web of orbiting infrastructure is not evenly distributed in space. Different categories of satellites occupy different orbital regimes, each with its own relationship to the space environment and its own specific vulnerabilities to solar activity. Understanding those vulnerabilities requires understanding that solar storms do not threaten satellites through a single mechanism. They threaten them through several different mechanisms simultaneously, operating across different orbital altitudes through different physical processes, and the combined effect of a major solar storm on the full satellite population is considerably more complex than any single factor analysis suggests. In low Earth orbit, which encompasses altitudes roughly between 200 and 2,000 kilometers, and is where the majority of newly launched commercial satellites operate, the most direct and immediately consequential mechanism is atmospheric drag. Earth's upper atmosphere does not end sharply at a defined boundary. It thins gradually with altitude, becoming extraordinarily tenuous in the range where satellites operate but never reaching true zero density. Satellites in low orbits are constantly experiencing a tiny but continuous braking force from the residual atmospheric molecules they encounter. Over time, this drag reduces orbital energy, causing gradual altitude decay. Operators compensate by periodically firing onboard thrusters to raise the orbit back to the intended altitude. This is routine satellite operations management, factored into mission planning and fuel budgeting from the outset. Solar activity disrupts this routine in a specific and significant way. The sun's extreme ultraviolet radiation heats Earth's upper atmosphere, and the intensity of that heating is directly tied to solar activity levels. During solar storms, extreme ultraviolet output increases substantially, depositing additional energy into the upper atmosphere and causing it to expand upward. The atmosphere does not get denser overall, it simply puffs outward, moving the same mass of gas to higher altitudes. For a satellite operating at, say, 400 kilometers altitude, this means the atmospheric density at its orbital location can increase by factors of 10 or more during a severe storm compared to quiet solar conditions. The drag force on the satellite increases proportionally. The rate of orbital decay accelerates. Thrusters must fire more frequently, consuming fuel reserves faster than mission planning assumed. And in extreme cases, the atmospheric density can increase so rapidly and so dramatically that satellites lose altitude faster than their propulsion systems can compensate, leading to uncontrolled orbital decay and atmospheric re-entry. The February 2022 Starlink incident is the case study that the space weather community returns to repeatedly, because it demonstrated this vulnerability with a clarity and specificity that no theoretical analysis could match. SpaceX launched 49 Starlink satellites into a low deployment orbit, from which they were intended to raise themselves to their operational altitude using onboard ion thrusters. Within days of the launch, a geomagnetic storm caused atmospheric density in low Earth orbit to increase significantly. The storm was a G2 event, moderate on the geomagnetic storm scale, not a rare extreme event, not a Carrington-class catastrophe, just an ordinary moderate storm of the kind that the current active solar cycle produces with some regularity. 38 of the 49 satellites were unable to generate enough thrust to overcome the increased drag and raise their orbits as planned. They re-entered the atmosphere and burned up, 78% of a freshly launched batch of commercial satellites, destroyed not by any dramatic failure of engineering or any exotic space weather phenomenon, but by the straightforward physics of air resistance, in an atmosphere that a moderate solar storm would push slightly higher than normal. The financial loss was in the tens of millions of dollars. The operational impact was a temporary reduction in Starlink coverage capacity, and the lesson was unmistakable. At higher orbital altitudes, different physical mechanisms take over. Satellites operating in medium Earth orbit, which spans roughly 2,000 to 35,000 kilometers, transit the Van Allen radiation belts, regions of magnetically trapped energetic particles that surround Earth. During major solar events, the particle population in the radiation belts intensifies dramatically as solar energetic particles are injected into the magnetosphere and trapped. Satellites passing through enhanced radiation belt regions experience increased total radiation dose, which gradually degrades solar panels, damages semiconductor components, and reduces the operational lifetime of electronic systems. The cumulative radiation environment over a satellite's mission lifetime is a fundamental design parameter, and a period of extreme solar activity can advance a satellite's radiation aging by months or years in a matter of days. Geostationary satellites, which orbit at approximately 36,000 kilometers and provide the fixed position coverage used for weather monitoring, television and radio broadcasting, and certain commercial communication services, face their own distinct vulnerability profile. At geostationary altitudes, satellites are exposed to the full flux of solar energetic particles during major solar particle events with minimal shielding from Earth's magnetic field. High-energy protons, accelerated to significant fractions of the speed of light during large solar eruptions, penetrate satellite electronics and cause what engineers call single-event upsets, events where an energetic particle passes through a memory cell or logic circuit and flips a bit from its intended state. Most single-event upsets are recoverable through software error correction. Some cause more significant anomalies, and in severe particle events, the cumulative effect of thousands of particle strikes per second can overwhelm error correction systems and cause permanent hardware damage. surface charging presents a related but distinct hazard. Different parts of a satellite's exterior accumulate electrical charge at different rates depending on their geometry, material properties, and exposure to the plasma environment. When charge differential between adjacent surfaces becomes large enough, electrostatic discharge occurs, essentially a tiny lightning strike within the satellite's structure. These discharges can damage electronics, corrupt data, and in severe cases disable instruments or entire subsystems. Satellite designers work hard to minimize differential charging through careful material selection and grounding practices, but the plasma environment during a major solar storm is substantially more aggressive than the nominal design environment, and margins that are adequate under ordinary conditions can be exceeded. GPS navigation deserves special attention because its vulnerability is distinct from the direct particle and drag effects that threaten satellite hardware, and because the systems that depend on GPS have proliferated to a degree that makes widespread GPS disruption a cascading infrastructure problem rather than an isolated inconvenience. The GPS signal travels from satellite to receiver through the ionosphere, the electrically charged upper layer of Earth's atmosphere, extending from roughly 60 to 1,000 kilometers altitude. Under normal conditions, the ionosphere is sufficiently uniform that the speed at which GPS signals propagate through it can be accurately modelled and corrected for. During solar storms, energetic particle precipitation and enhanced solar radiation create ionospheric disturbances, irregular variations in electron density that cause the GPS signal to travel at variable speeds along different paths, introducing errors in the calculated position that the standard corrections cannot fully account for. During a severe geomagnetic storm, GPS positioning accuracy can degrade from the normal few-meter range to errors of hundreds of meters or more. Aviation precision approaches, which require GPS accuracy within a few meters to guide aircraft safely to runway thresholds in low visibility conditions, must be suspended. Container ships navigating narrow channels, autonomous agricultural equipment, surveying instruments, and the timing systems that synchronize financial transactions and telecommunications networks all operate with dependencies on GPS accuracy that most users never think about until the accuracy is gone. The full picture that emerges from examining these mechanisms together is one of layered, interconnected vulnerability across an orbital infrastructure that modern civilization has built with extraordinary speed and come to depend on with very little systematic assessment of what a major solar event would do to it. And the trajectory is moving in the wrong direction from a risk management perspective. Every year the satellite population grows, every year more applications are built around GPS precision, every year more critical services migrate to satellite-dependent infrastructure. Every year the exposure increases while the space environment is demonstrating in the current active solar cycle that it is more dynamic and more capable of disruption than the relatively quiet preceding decades suggested. The February 2022 Starlink loss happened during a G2 storm. The May 2024 G5 storm affected satellite operations across multiple commercial networks simultaneously. The 2012 CME, had it struck Earth directly, would have hit a satellite population far smaller than today's, with far less of the critical infrastructure we have since built around it. The satellite constellation that exists today, the one that 10,000 active spacecraft serve, the one that GPS-dependent systems across every sector of the economy rely on, has never been tested against anything close to a Carrington-class event. An Miyake-class event would be in a category that no satellite engineer has been asked to design for, because no satellite engineer alive has ever seen one, and neither has anyone else. The star overhead is getting more active, the infrastructure below it is getting more dependent, and the gap between those two trajectories is not closing. Part 15. The final question. Humanity hasn't answered. Let us come back to where we started. A G2 geomagnetic storm is affecting Earth right now. Aurora is visible over New York. Solar wind is moving at 700 kilometers per second. An active sun is producing flares and coronal mass ejections at rates that exceeded every prediction made before this solar cycle began. And somewhere in the French Alps, in ancient pine wood older than any written human record, the chemical signature of something much larger than all of this sits preserved in carbon, dated to approximately 14,300 years ago, waiting for us to fully understand what it means. We began with a storm, we end with a question, and the question is more unsettling than the storm. Over the course of this story, we have established something that deserves to be stated plainly before we go any further. The Sun does not need to do anything new, anything unprecedented by its own standards, anything outside its demonstrated historical range of behaviour to end the technological civilization humans have spent the last 2 centuries building. It only needs to repeat what it has already done. The Carrington event of 1859 was not an anomaly in the Sun's long record. It was a moderate data point in a distribution that extends considerably further in both directions. The 2012 CME, which missed Earth by 9 days and would have struck a world far more dependent on vulnerable technology than the world of 1859, was potentially stronger than Carrington. The 774 Miyake event was 10 to 20 times Carrington. The 14,300-year event preserved in sub-fossil pine rings from the French Alps was in yet another category entirely, one that our instruments have never directly measured and our infrastructure has never been tested against. The Sun has a range. We have been living in one of its quieter intervals, building everything we depend on within the tolerances of that quieter interval, and treating those tolerances as permanent features of reality rather than temporary luck. The power grid problem is the most studied, the most concretely quantified, and in some ways the most tractable component of solar storm risk. The mechanism is well understood. Geomagnetically induced currents flow through long transmission lines into transformer systems not designed to handle them. Transformers overheat and fail permanently. Replacements take years to manufacture and deliver. Grid failures cascade across interconnected regions. Recovery stretches from months into years. The cascading consequences: water systems, food supply chains, hospitals, fuel distribution, communications, degrade simultaneously and continuously throughout that recovery period. This is not speculation. This is the documented engineering analysis of what happens when you combine a large geomagnetic storm with the specific vulnerabilities of high-voltage power transmission infrastructure. And here is what makes this particular risk so frustrating to anyone who has spent time looking at it carefully. The cost of meaningful protection is not prohibitive. Installing geomagnetically induced current blockers on the neutral connections of high-voltage transformers at the most critical substations is an established engineering solution with known costs and known effectiveness. Building a strategic reserve of spare extra high-voltage transformers, not enough to replace everything, but enough to restore the most critical nodes of the grid after a major event, is a logistics and procurement challenge, not a physics problem. Developing standardized, pre-planned protocols for rapid protective grid loading reductions during space weather alerts, coordinated across utility boundaries and regulatory jurisdictions, is a policy and operational challenge that organizations with the will to address it have the tools to address. None of these solutions are waiting for a scientific breakthrough. The knowledge exists. The engineering capability exists. What has been insufficient consistently and across multiple administrations and multiple countries is the sustained political will to prioritize this work against the constant competition of other infrastructure demands, other budget pressures, and the deep human tendency to discount risks that are possible but not scheduled. The internet resilience problem sits in a more difficult category for reasons that have less to do with engineering and more to do with the structure of the systems involved. Undersea fiber optic cable networks are privately owned, internationally distributed, regulated by frameworks that were designed around commercial and security concerns rather than space weather risk, and physically inaccessible for modification once deployed on the ocean floor. You cannot retrofit a repeater station sitting under 4 kilometers of Atlantic Ocean. The vulnerability that Sangeetha Abdujyothi's research identified, the susceptibility of long undersea cable systems to geomagnetically induced current damage during extreme geomagnetic storms, is a vulnerability that cannot be addressed through the kind of targeted hardware intervention that works for power grid transformers. Addressing it requires designing future cable systems with better protection, developing operational protocols for managing traffic routing during severe space weather events, and building redundancy into international connectivity at a level that current commercial economics do not naturally incentivize. None of this is impossible. All of it requires coordination across private companies, national governments, and international regulatory bodies that do not currently have frameworks in place for it. Awareness, as we noted, is the necessary first step. That awareness has grown since the research was published. The steps beyond awareness have not yet followed at the pace the risk warrants. The satellite risk is in some ways the most structurally complex to address, because it is not amenable to a single protective measure or a single policy intervention. It requires a rethinking of how orbital infrastructure is conceived, designed, and operated, a shift from the current paradigm of launching minimum viable operational constellations to a paradigm that builds genuine resilience against an environment that can become catastrophically hostile on timescales, ranging from minutes to days. Satellite constellations designed for solar storm resilience look different from satellites designed for cost efficiency in a benign space environment. They carry more radiation shielding, they carry more fuel for orbital management, they are designed with more redundant systems. They are launched in numbers that allow a significant fraction of the constellation to be lost in a severe storm event while still maintaining service continuity. These design choices cost money, they add mass, they complicate launch economics. And in an industry where commercial viability depends on aggressive cost management, they are choices that market forces alone will not reliably produce. Regulatory frameworks, insurance requirements, and government procurement standards that incorporate space weather resilience criteria are the levers through which these design changes could be driven at scale. Those frameworks are in early stages of development in most jurisdictions. There is something worth pausing on in where this story arrives, something that sits at the intersection of science and philosophy and the particular character of the moment we are living in. We inhabit a civilization of extraordinary capability. We can read the genetic instructions of any living organism. We can detect the gravitational ripples produced by two black holes colliding 1 billion light-years away. We've built machines that can master any game humans have ever invented, translate any language, and increasingly assist with problems that were previously the exclusive domain of trained specialists. We understand, in considerable and growing detail, the physics of what the sun does and why it does it. We have found the evidence of what it has done in the past, preserved in tree rings and ice cores and the isotope records of ancient wood, and we have calculated with reasonable confidence what similar events would do to the infrastructure we depend on today. We are not ignorant of this risk. We are not waiting for knowledge we do not yet have. We are in the unusual and uncomfortable position of knowing what the threat is, knowing what it would cost to address substantial portions of it, and having thus far not addressed them at the scale and speed the risk profile suggests is appropriate. The early warning systems are improving, and that is genuine progress worth acknowledging without qualification. The science is advancing, the AI forecasting tools are getting sharper, the political awareness is growing in ways that would not have been true a decade ago. Space weather preparedness appears in national security frameworks and international policy discussions in ways that reflect a real shift in institutional understanding of what is at stake. These are not nothing. They are meaningful movements in the right direction. But the sun does not operate on a human schedule. It does not wait for preparedness reviews to complete their comment periods. It does not pause while infrastructure budgets work their way through legislative processes. It does not postpone its most extreme behaviour until international coordination frameworks have been negotiated and ratified. It operates on solar physics timescales, driven by the dynamics of a magnetic dynamo in a star 4.5 billion years old, and those dynamics are indifferent to our administrative calendars and completely unimpressed by our policy intentions. The 14,300-year event happened. The 774 event happened. The 2012 near-miss happened. Each of these is documented, measured, published, and available for anyone who wishes to understand the sun's demonstrated range of behaviour. The record is not hidden. The physics connecting that record to the vulnerabilities of modern infrastructure is not obscure. The engineering solutions to the most addressable portions of the risk are not secret. What remains unknown is not what the sun can do. The sun has already shown us what it can do. Written in carbon and preserved in wood older than every human civilization that has ever risen and fallen on this planet. What remains unknown is the answer to a different question entirely. When the sun does it again, not if, because the historical record does not support if, only when. Will we have spent the years before that moment doing the things we already know how to do? Will the transformers have their protection systems? Will the spare parts exist in the warehouses? Will the protocols be rehearsed and the operators trained and the warning systems staffed? Will the satellite constellations be designed for the environment they actually orbit in, rather than the environment we found convenient to assume? The Sun's behaviour is outside our control. Our preparation for it is entirely within our control. That distinction is the most important thing this entire story has to say, and what we do with it, in the years between now and whenever the Sun decides to remind us of its range again, is entirely up to us.